Syntax builds the form we see. Semantics gives it meanings key. Connectives link what minds devise. Quantifiers range through truth and lies. Modus ponens strikes with might. Modus ponens flips the fight. Logic cuts clean, no shallow line. Through the long night, reason shines.
Previously, we have discussed the negation of a statement involving multiple quantifiers. Now we discuss the order of quantifiers. If both quantifiers are of the same type, then, using the rules of inference we developed earlier, it's easy to see that the statement doesn't depend on the order. But things get trickier when we deal with mixed quantifiers. In that case, the statements may not be equivalent. To see this, consider two examples. Let A and B both be the set of all cats, and let Pxy mean y is the father of x. The first statement says, every cat has a father, which cannot be more reasonable. The second says, some cat is the father of all cats. In other words, we are claiming the existence of a godcat. Let A be the set of locks and B the set of keys. Let P, x, y mean y opens x. Then the first statement says, every lock has its own key, while the second statement says, there is a master key that opens every lock. Again, these statements are not equivalent. Needless to say, if we have a master key that can open any lock, then each lock has a key. Just use the master key for each lock. Indeed, given the true premise, there exists y such that for all x, p, x, y, we can first deduce, by existential instantiation, that for some c in the domain, the statement for all x, p, x, c is true. It follows that for an arbitrary instance x, the statement px, c is true, due to universal instantiation. Next, by existential generalization, this in turn implies that there exists y such that px, y. Finally, since x is arbitrary, by universal generalization, we conclude that for all x, there exists y such that pxy is true. Be careful. The other way around may not hold. We use the following examples to illustrate this. Consider the statement. For any real number x, there exists a real number y such that y minus x is greater than -2. This is true. To prove it, let x be an arbitrary real number and take y to be x. Then y minus x is equal to 0, which is greater than -2. On the other hand, if we exchange the order of quantifier, then the thus obtained statement is false. To prove it, consider its negation, which reads, for any real number y, there exists a real number x, such that y minus x is less than or equal to -2. This is true. Indeed, let y be arbitrary and take x to be y plus 3, then y minus x is equal to -3, which is less than -2. Hence the original statement is false. Consider the statement, for any integer x, there exists an integer y such that x plus y is divisible by 2. This is true. To prove it, let x be an arbitrary integer and take y to be x, then x plus y is equal to 2x, which is divisible by 2. On the other hand, if we exchange the order of the quantifiers, then the resulting statement is false. To prove it, consider its negation, which reads, for any integer y, there exists an integer x, such that x plus y is not divisible by 2. This is true indeed. Let y be arbitrary, and take x to be y plus 1. Then y plus x is equal to 2y plus 1, which is not divisible by 2. Hence the original statement is false. Let us summarize our discovery. When the universal quantifier comes before the existential quantifier, the statement is generally less demanding. The choice of y can depend on the given x. As x varies, y is allowed to vary accordingly. In contrast, when the existential quantifier precedes the universal quantifier, the statement becomes more demanding. The choice of y must be made once and for all, independently of x, This single y must work for every possible x. In other words, the second form requires a kind of uniformity, like a god cat bringing life to all cats, or a master key that can open all doors. You have now seen how the order of quantifiers can impact the truth value of a statement with nested quantifiers. We will encounter this subtle distinction again when we study various topics in mathematics, for example, pointwise versus uniform continuity of functions, among many others.
信了，ten say。